Hi, it's Mr. T here. Today I'm going to go over the concept of vertical circular motion. This is part of the mechanics topic in level 3 physics. So, so if we look at the a vertical constant motion under constant velocity, that means if I have an object like this motorcyclist going around the inside loop of this track, they would go at the same velocity at all points around the loop. And you can imagine this if you were held on a small bucket full of water or sand and you just looped it around with your arm, okay, and you could make your arm go so that the bucket was going at a constant velocity of all times. So when we have a constant velocity of an object going around in vertical motion, then we say that the centripetal force stays constant as well. Because you need to imagine that the equation for centripetal force equals the mass times velocity squared over the radius. If the mass stays the same, which it will, and the radius stays the same, which it does, if it's a fixed circle that it's going around, and the velocity stays the same, then nothing has changed and the centripetal force must stay the same. So the centripetal force must be equal at all points of the circle because the velocity is equal at all points of the circle. Now, the force due to gravity is also constant throughout the journey, and it's always the mass times 9.81 directly downwards. However, only an aspect of the gravity force will contribute towards the centripetal force. This centripetal force is a force that is actually produced by other forces. And the two forces that would make this centripetal force are called gravity and a support force or a reaction force. If you look at the top here, you can see gravity is, if we just took gravity, it could produce the top force. But if we took gravity on the side here, because it's going directly down, it doesn't contribute any sideways gravity that would contribute to this gravity force. So this this centripetal force, so that has to come from somewhere else. In any way, what we can do is we can say what parts of this gravity are acting parallel towards the center or in the same direction or the opposite direction to centripetal force. You can see that all of this acts towards the center, all of the bottom one act parallel away from the center. When we get to this point here, if we just look at an example here, you can see, oh no, I don't have that example right there, but if we look at this point right here, I could actually draw a right angle triangle with this gravity, and I can draw a component that goes parallel with the centripetal force at A and a component that goes perpendicular. It's only the component that goes parallel that contributes towards the centripetal force. If we look at point A on each of these diagrams, you can see I've drawn the component of gravity that contributes towards the centripetal force. It actually goes against the centripetal force. So the reaction force or the support force of the track needs to add to the gravity force, which is in the opposite direction, to produce the centripetal force. So we're adding these vectors, so we're adding the gravity and the support force to equal the centripetal. So because the gravity force is acting in the opposite direction to the centripetal force, our reaction force has to be a lot bigger. Okay, so let's look at let's have a look at some forces that are acting at 3 different points on a vertical circle. So it's important to know that, and I'll say this again, I said it before, that the reaction force or the support force, let's just call it the support force, but I write a Fn here for the normal force, plus gravity is what produces our centripetal force. Our centripetal force isn't an actual force, it's a combination of the support force and the gravity force. So I'll show you what I mean here. Let's have a look at this example here. So this example, at this point, the centripetal force is acting directly downwards. There is a gravity force that only goes that far, produces a certain amount of the centripetal force. The extra force needed to turn this motorcycle around has to be provided by the normal or the support force from the surface of this loop. So it pushes on the bottom of the cyclist or the motorcyclist to produce the extra bit of force needed to produce the total amount of centripetal force to turn this object. So however much centripetal force is needed in this loop at that velocity to turn has to be provided by the forces that are available. If there isn't enough gravity force, then the extra force is made up by the reaction force or the support force of the surface that the motorcyclist is traveling around. Let's look at the next example. So in this example, the centripetal force is acting directly to the center. Now have a look at the gravity force over here. It's acting directly down, the same size as before, but because it's acting perpendicular at right angles to the centripetal force, it provides no component or no magnitude in the direction of the centripetal force. So the force that needs to supply all of the force to produce the value needed for our centripetal force, it has to all come from our support force, from Fn. So Fn produces all the force needed to make this motorcycle go round in a circle. Let's have a look at the last example here. In the last example, the gravity is acting at an angle to our centripetal force, so it has a part of it that is acting parallel to the centripetal force, and that component can be calculated using trigonometry or right angled triangles. So the gravity force Fg equals mg. A lot of the times when we write a gravity force, we can just write mg because that is the equivalent from the formula of the force of gravity. So mg is our hypotenuse here, but our adjacent to this angle is the component that we need to work out how much of this support force is needed to provide the centripetal force. So I can use this formula. This is a cosine formula from trigonometry. So the adjacent equals the cosine theta times mg. Now if we look at the forces that are involved here, we have a centripetal force that needs to be produced going that way. However, gravity is going the opposite direction, the component of gravity that's acting parallel. So now our normal force or our support force has to provide enough to overcome the gravity going in the opposite direction and enough to produce the centripetal force. So it is a lot bigger than the original centripetal force. And in fact, at the bottom, it is the biggest that it can possibly get. It's double the centripetal force, which is why we get the phenomenon at the top. When we're at the top of one of these loops, we only feel a wee bit of pushing from the ground, and that is a feeling that we feel as weightlessness. We don't feel much weight being pushed upon us. So we feel like we are falling through the air when we're at the top here, when the support force is very small. At the bottom, when the support force is a lot bigger than we would normally feel from our gravity force, we would feel heavy, we feel pushed down. And you feel that sometimes when you drive down into a dip, you can feel heavier, and when you drive over a bump or a hump, you can feel that you feel a bit queasy, or you feel a bit like you're falling through the air but weightless. So we can get a certain situation that happens is if you're going at a constant velocity, there is an actual point where the gravity force will provide all of the centripetal force. Now that is the smallest possible speed that you can go around here, okay, and not fall off. So the centripetal force will equal the gravity force when you have your minimum possible velocity you can go around the loop without falling off. What's happening is all of your gravity force is producing the centripetal force, and you don't need any support force, and you would feel completely weightless at the top, like you were falling through the air. You're not, because you're still getting turned. The gravity is turning you round the circle, but it would feel like that. So at this boundary condition, when the minimum velocity equals when the centripetal force equals the gravity, that is the minimum possible velocity you can have going around this loop. Now, if I put these two values, these quantities together, I can substitute in what they're equal to, their equations, right? We know Fc equals mv squared over r and Fg equals mg, so I can substitute those in. I can then cancel out the m's. I can take the r from the denominator and move it to the other side and put it on the top here, multiplied to g, and then I can square root both sides and I get this rearranged equation to calculate what is the minimum velocity to get around a loop. The minimum velocity is equal to the square root of gravity times the radius. So here's an example. Here's our motorcyclist. Well, I'll say our cyclist here. They've got to work pretty hard to get around a loop if they're a cyclist. They need to maintain, what is the minimum velocity that they need to maintain in order to get around the loop without falling off? So we're going to use the same equation that we derived in the previous slide. The loop is 12 meters high, I think. Okay, so we derive, substituting the equation, we rearrange it, and now we put the values in. Now notice I've put the gravity in as 9.81, that's the gravity constant, and I've put the radius as 6 because we said the loop was 12 meters high, so the radius of the circle is 6 meters. And we get the value of 7.7 meters per second. That is the minimum speed that you have to get around this loop. If you went slower than 7.7, you would actually fall off this loop and fall down, and you wouldn't make it round the other side. If you went at least that velocity, you would stay on the track. If you went faster, you would stay on the track, but you would start to feel some pushback from the track, and it would feel like gravity when you stand on the ground. Okay, so here's another situation. So that was when we have constant velocity. Now we're going to look at, well, what if we don't have constant velocity? And this happens a lot of the time. So this is a mountain biker or a cyclist. They're going to go down here and they're going to go around the loop. Now, what we can see is that we know that they have energy at the top and they're going to have energy around the loop. Now the whole crux of this idea is that we can solve problems by the energy they have at different situations. So at the top of the loop here, the total energy that this cyclist has is equal to the potential energy that they have, which is equal to their mass times their height times gravity. So the height is the height from the top to the lowest point. So I could work out the total energy if I knew the height, the gravity, and the mass. When they're at the bottom here, when they come down to the bottom, they have lost all of their height. They no longer have any of their potential energy. It's all been transferred into kinetic energy. So I know now that at the bottom, the total energy here is equal to their kinetic energy, or is equal to half mv squared. If they continue to go up the loop to the top here, then obviously at the top here, they're not as high as they originally were. When they get to the top here, if they are unable to, if they're not motorized, if they don't put more energy in as they go up, what will happen is they'll be really fast at the bottom, but as they get to the top, they slow down and they go around and they speed up again as they go to the bottom, because at the top, the kinetic energy has been turned into potential energy, and at the bottom, the potential energy is turned into kinetic energy. However, once you get to the top of this loop, you still have some kinetic energy because you need that to get around, but you also have some potential energy from the difference in height from the top of here to the top of here. So the total energy is still the same, but it now has potential energy, the mass times g times height, but the height now is the difference in height from the start, this distance here. And its kinetic energy is its velocity times its mass times half squared. Oh, sorry, times half. Right, so that's what it does. Cyclist starts off here with potential energy, goes to the bottom with kinetic energy. Its maximum kinetic energy is always at the bottom. As it goes up here, some of the kinetic energy is turned into potential energy, so when it gets up to here, it is now traveling slower because it's bleeded off that potential energy, but it has some potential energy, it's just been converted, and it still has some kinetic. And when it falls back down to the bottom again, it all goes back into kinetic energy. So how do we use this? Well, we can solve a problem with this. So here is my cyclist here, they're about to go around this loop. And the loop has a radius of 10 meters. And remember we said that the total energy equals potential energy at the top, the total energy equals kinetic energy at the bottom, and the total energy equals kinetic energy plus potential energy in the middle. So the very first step I can do is I can look at this loop and I can go, what is the minimum velocity they need to get around the top here? And we use this equation we derived before. V equals the square root of g times r. And we work out here that the minimum velocity you need to get around this loop is 9.9 meters per second. So that's good, because once I know the minimum velocity, I can calculate the kinetic energy at the top. So I can calculate the kinetic energy at the top by multiplying the mass times half times the velocity squared. And I get that at the top of this loop, the kinetic energy that the cyclist will have is 3,924 joules. But I can also work out what the potential energy at the top of this loop is, because I can see here that the cyclist is 10 meters plus 10 meters, 20 meters above the lowest point. And I can use EP equals MGA to calculate the MGH, to calculate the potential energy. So we can take 80 times 9.8 times 20 equals 15,680. That's how many joules of potential energy. So they've got this much kinetic energy, but that much potential energy. And guess what? Remember we said before that the total energy never changes. So at the top of this loop, if they have kinetic energy and potential energy, we can add these two together and they will give us the total energy that the cyclist has at the top. Now let's say that again. At the top here, the total energy is the same as at the bottom, and it's the same as up here. It never changes. So if I want to know what is the minimum height the cyclist has to be here, I know that at the minimum they need that much energy, 19,604 joules of energy. That's how much energy they need in order to have the velocity to get around the top of this loop. So now I know that energy. I also know the height here. Sorry, I don't know the height. I know the gravity and I know the mass. So I can actually just use this equation here. So I can use this equation, EP equals MGH. I rearrange it. I take M and G, put it on the other side on the bottom. So H equals EP over MGH. I take that total energy, I divide it by the mass and the velocity, and I work out, well, the person has to start at least 25 meters at the top, higher than the bottom, in order to get around the loop. Now, of course, this is if there is no friction. But we know there would be friction. As they go down, they will lose some energy to heat from friction from their bicycle. So if they went at 25 meters, we know there would be friction and they wouldn't make it. However, if it was a perfect world and there was no friction, 25 meters would be the smallest height. Okay, look, if I wanted to do this as a trick, I think I would make sure I was at least 40 meters, because I don't want to take it 25 meters and find out I'm going to fall off. Okay, one more example here, and this is commonly happens, and this is someone who's just going over a wee hillock, right? They're on their cycle and just been biking up a hill and they're going over the top. Now, you can imagine if someone went fast enough, they could go up this hill and they could do a jump off the edge. What is the speed that you have to be at in order to not stay on the ground? This is another vertical circle question, circular motion, but it's actually on the outside of a loop instead of the inside of a loop. So to stay on the ground, the gravity force needs to be bigger than any centripetal force that you would need for the circle. So the key thing here is we need to find out what is the centripetal force we need for the circle. And if we know the centripetal force, we can then go, well, what is the velocity needed to provide that centripetal force? If we get larger than that velocity that was needed for the centripetal force, the gravity will not provide enough force for our centripetal force, and we will not be able to follow the circle, and we will jump off the top. So how fast does the cyclist have to go in order not to leave the, well, in order to leave the ground, or not to leave the ground, I guess. In order to leave the ground, the centripetal force needs to be bigger than, no. In order to leave the ground, the centripetal force needs to be bigger than the gravity force. Oh, I guess that's right. So, let's find the boundary here. So we're going to put the centripetal force equal to the gravity force. At what point, well, what velocity does that equal that? So we substitute in the two equations here, cross out the masses because they're on both sides. So the mass actually isn't important here to work out. It's just going to be, what's going to be important here is the velocity, right? So velocity squared equals the radius times gravity. So velocity equals the square root of radius times gravity. And we get this value here. The velocity is 47 meters per second. So if you went faster than 47 meters per second, then the centripetal force you would need would be, if you were faster than that, then your centripetal force would be bigger than your gravity, and the gravity would not be able to provide enough force to pull you down. If you went slower than that, then your centripetal force would be smaller than gravity, and gravity would provide enough force to pull you to the ground. That is the limiting condition. Just about every single question we have about this will be finding the boundary. What is the point in which you would leave the ground, or what is the minimum speed that you would have to get around the loop? And this is the focus on most of the questions on vertical motion. Okay, thanks for listening to the video. And I will stop.